Hello everyone, let's solve a new problem today. Search in rotated sorted array. Let's read the problem. There is an integer array nums sorted in ascending order. Okay, this is an already sorted array with distinct values. Prior to being passed to your function, nums is possibly rotated at any unknown pivot index k, where k lies between 1 and nums length. Okay, such that the resulting array is nums k plus 1 up till end of the array and minus 1, and then nums of 0, nums of 1 till nums of k minus 1. Understood? So this is just a rotated array. For example, 0, 1, 2, 4, 5, 6, 7 might be rotated at pivot index 3 and becomes 4, 5, 6, and digit. Given the array nums after the possible rotation and an integer target, return the index of this target if it is in nums or minus 1 if it is not in nums. You must write the algorithm in log n runtime complexity. Okay, so one of the brute force ways would be just iterate through it, find out if it is present. The only problem it will be linear time complexity because we have to iterate through it once. Okay, for log n, the first thing that comes to our mind is binary search, right? Now, generally in binary search, you would be given a sorted array. You'll um, grab the middle index, see where we are, based on that go left or right, right? Here the only problem would be binary search would work properly if the array is fully sorted from it needs to be the smallest number, let's say, is in the beginning and the largest is at the end of the array. Here, because it is rotated, we would have to do something about it. We'll think about it. Let's say, let's take few examples. Target 0, output would be 4. Target 0, output is 4. Target 3, what is this, right? Return the index of target. So target 0, what is the index of this value? 0, 0, 1, 2, 3, 4. That's why it is 4. Okay, target is 3, 3 is not available, that's why output is minus 1. Target is 0, it is not available, this is minus 1. Nums length, the length of the array is 1000, well, 5000. All the values of nums are unique. 5000, if it is 5000, even linear search would work. Okay, but because they have written this, yeah, so we are going to think about a binary search. But just to prove it, because the nums length is 5000, we can actually do a simple linear search. Let's try that. Brute force. 0 is less than nums length I plus if nums of I equals target, you return I. That would be all, otherwise minus 1. That's all. That is it. Accepted, 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 all the three cases, and it should work even on submission. But maybe, yeah, maybe during yeah, it got accepted because the size of the arrays, okay, is 5000, right? It is going to work. Well, let's solve this in big O of log and time complexity now. Let's try to identify what we can do. So let's understand binary search and then what we can change in our normal binary search to solve this problem, some kind of altered binary search. So generally, let's say this is a sorted array, smallest number uh, in the beginning, and this height just represents the value of the number, right? The larger the number, the more height this arrow will have. So this is sorted. Now if we have to find a number, say 23, what would binary search look like? This is our 0th index. This is our final index of the array, that is n minus 1. So we get to the midpoint, the middle point of this array. Okay, so our in normal linear iteration, what we would have done, what we did in brute force, we checked the first index, then we moved to the next one, we moved to the next one, we moved to the next one. We kept on doing this till the time we found this number 23, right? And because we had to do this n times, size of the array is n, that's why its time complexity is big of n. Now here we want to make few changes. Instead of this linear iteration, our approach would be get to the middle, see what value is kept here. The two options would be the value in the middle. So we'll say this is mid. The value in the middle is going to be greater than 23 or less than 23. Now we have two directions here. If the value in the middle is greater than 23, then in the array we have 20, possibly we have 23 in the left hand side, right? Because the current value is higher than 23, and because this is ascending order, so 23 is possibly in the left hand side. Why possibly? Because either 23 would be there in the left hand side, or if 23 does not exist in the array, we just have to return -1. Still, the only way to search is search in the left hand side, because we are certain that in the right hand side of this middle element 23 will definitely not be there, right? So we had mid, and let's say the value at the mid is 43 or a number higher than 23, and that's how we know that our new domain, our new area to explore the number 23 is left hand side, that is 0 to mid -1. So we can think of that area of interest in the beginning was 0 to n -1. After that, we had two options. Our area, let's ignore this. Let me remove this. Two options. The area of interest is 0 to mid -1 or mid +1 till end of the array. The reason why we are not focusing on mid is if we found 23, the number which we were finding on the mid, we are just going to say that okay, we have found a number, we are just going to return from it. So when we had 0 to n -1, the area of interest, then we were focusing on the mid element. Now we are clear that okay, on array of mid our number is not there, we go with one of the options. Let's say we went with this one, so 0 to mid -1. Again we do the exact same thing in this new array 0 up till mid -1. Again find the middle point of this array. Again search for the number, okay, if this number is greater than, less than or equal to 23. If let's say this number at the mid is 15, a smaller number, right? So we know that okay, at mid, at this point which we have already take removed, because we know that mid is not 23. So this mid number was let's say a higher number which we wrote here 43. That's why we went to the left. Now in this area we know that the current number is 15, so and this is sorted, so our number 23 needs to be in this area, right? Smaller than previous mid but greater than new mid. And in this way we had again two options to go from here. The first option was 0 to the new mid, so I'll call it mid, capital MID, let's call it this MID, right? This one, or the same step, mid +1, and we keep on doing this till the time we are left with either one element or no element. We'll look at that. And yeah, so this is our normal binary search. Now let's talk about a new altered version of it. Hmm. Let me remove this. So in our case, we are saying initially the array was sorted, and then we are rotating it. I'm just checking if there is a mention of this rotation is clockwise or anti-clock or something like that. See, it was 0, 1, 2, 4, 5, 6, 7, so they moved it ahead. Okay, so understood. So basically this array will keep on increasing till a point and it will reduce. Okay, sure, sure. So when it is rotated, how it would look like is, let's say we chop this actual array on this pivot point, and then we just move it here, the right hand side to the left and the left hand side to the right. How it would look like? It would look something like this, and then we'll use this point, this, right? So we can see that actually we can do binary search, because just that instead of searching, doing the binary search across the complete array, we are going to do it on the first array, because this is ascending order, this is completely fine, sorted, and then this is the second array, right? Yes, so we'll do normal binary search on array 1 and array 2. So our initial problem now splits into, instead of doing a binary search on this array 0 to n minus 1, we do it on, let's say this is pivot, we do it on 0 to pivot as the first array. Actually calling it pivot might not be right, so let's call it any boundary index, boundary index, right? When things change, boundary index. Make sense? So 0 to boundary index and then boundary index up till end. Okay, sure, sure. So what are the things we will be doing? First is find the boundary index, define the two sorted arrays. By define, I just mean we just have to define the boundaries. Okay, uh, the first array starts from this point and gets to this point, and the second array starts from this point, gets to this point. Fine. Third is do binary search in both arrays independently. That means we are going to do the binary search in the first array. We find the element, that's good. We do not find it, then we go for the second array. We again find it. This one is going to be log of, let's say this was complete size was n, and this area was of size a. So this is of size n minus a, right? So this is n minus a and this is a. So this one is going to take log of n minus a time. This is going to take log of a time, right? So you just add them, and still it is logarithmic time complexity. It is going to be roughly log of n. That's okay. Cool. So we have found a technique. So let's go through these steps one by one in code. Find the boundary index. What will be the boundary index? The first time we get smaller element, right? The first time, so we keep on increasing the size of the element keeps on increasing. Suddenly there is a drop. We have to identify the index when we get that drop. Okay, I'm just thinking, is there a possibility that we'll never see that drop, right? But we'll get there. So let me just remove this. Okay, so our first step is find the boundary index. Find the boundary index. Boundary index by default we are going to keep it at minus 1, right? Sure, we'll see. And then we just iterate through the array. Dot length I plus plus. And we are saying if this element, the next, or you can even say current element, if the current element is smaller than the previous element, that is when we know that current element is a boundary case. So if nums of I is less than nums of I minus 1, right, we know that it is our boundary index and we have to break. Now the problem is, because it is I minus 1, iteration starts from I is equal to 0, so it is going to create a problem, right? Negative index exception is going to be thrown. So we have to start from I is equal to 1. Yep, yep. And here it is even written, I saw it somewhere, wait, nums length, nums all the nums digit, target is to the modifier. I think there will always be one rotation, isn't there? Prior to the pass to an unknown pivot index, k lies between 1 and nums of length. Okay, yeah, that means pivot index will always be there, right? There will be a rotation, we'll see. Yeah, so we are saying iterate through it. The first time we encounter a smaller element compared to the previous element, we have found the boundary index and break out of it. Sure. Now what's next? We have to define the two sorted arrays. Okay, so before defining the two sorted array, shall we just, because at the end we have to do mind research, so we'll just write a code for mind research. Public int binary search will be given an array, will be given a start index, an end index, and the target. What we have to do is, yeah, start index, end index. We keep, I'm just thinking, shall I, let's do this. While start index is less than end index, we find out the mid, that is start plus end minus 1 and minus start plus 1 divided by 2. Let me quickly check this. Sure. Find out the mid, and then we do if array of mid equals the target. If it is equal, we have to return target index. By default, we'll keep it as minus 1. Array of mid equals target. We have found the target index, and that is going to be mid, and we break out of the loop, right? We break out of the loop. Yeah, else if array of mid is greater than target, then we have current value is higher, we have to go left. So we do end equals mid minus 1, right? Our right end needs to go 1 before mid. Sure. And final one is else, we'll make it more structured, else start is equal to mid plus 1. Because it is not that readable, I'll do this. Array of mid is less than target if and else, we'll just grab this and put it at the end. Okay, cleaner. So if array mid is greater than target, we do this, otherwise start, otherwise this, and we are at the end. And at the end, we just return our target index. The thing is, only when we find this value, we are going to uh, have -1 assigned, non -1 value assigned to it. Otherwise, by default, it is going to be -1. Sure. Our binary search is ready and it is going to return an index. Fine. Let's move to the next state, that is define the sorted arrays. Okay. So let's say our target index is binary search. I'm defining the first sorted array. It will start from 0 and the end point is going to be boundary index -1. -1. Why? Because this point where we just moved from a very high value to the low value, this low value point is the boundary index, right? So we have to do 0 up till boundary index -1 for the first sorted array. And our next search option would be, so let me call it in target index left, and then int target index right is just binary search on the right array, that is boundary index till the end, boundary index till the end of the array, right? Let me think. Sure. Okay, boundary index. I'm just thinking, should we, what if the boundary index comes out to be -1? That is, there's never a drop. We never move from a very high value to a low value. It always is ascending in nature. In that case, it is a normal sorted array and we should do one proper binary search. So the default value should not be -1, it should be nums dot length, right? So in this way, our first binary search will automatically pick the boundary index as the first array is 0 up till nums length -1, that is the whole array, and the second one we can just ignore. Okay, so what we'll do is we'll get to that. Search we'll do a little bit of sanity check here. If start is less than 0 or end is greater than equal to array dot length return -1. Just sanity check on binary search, and at the end, do we have to do binary search both the times? If we find the number in the first array, we do not have to do the second time, right? So we'll do target index if target index left is not equal to -1. I'm getting a call, that's okay. If target index left is not equal to -1, we just return target index left. Otherwise, we go with this and we return. We'll improve the code. Target index right. We find the first one. If it is not -1, we just return it. Otherwise, we search for the element in the right array, and we find out the target. Yeah, let's run this. We'll see. Expected. Let's have. Oh, sorry. Line number 17, few some syntax error is there. Let's see. It is saying I do not have ARR binary search on nums. Binary search on nums. It does not exist. Line number 22 to okay. Target. We have to specify target as well, right? Target and target. We are done with syntax error. Now we'll see the actual error. So few cases, target 3 output is -1. So the -1 did work. There's some problem here. Output target is 0. Output we are getting as -1. Expected was 4. Interesting. Let's find out why. Let us try to understand. Let's just scan through the code once. Boundary index is this. I is equal to 1, I is less than. So if we look at this array, I starts from 1, nums I. The first time we get the current value smaller than the previous value, and that is this one. So our boundary index has correctly been plotted, right? This one. And then we are doing binary search 0 up till 0, that is this 4, up till boundary index -1, that is 7. So this array, the first array with a target of target, that was target is 0, right? And the second array is boundary index up till nums length -1. So 0, 1 and 2, this is our second array. Okay, so we have defined it correctly. Most probably the problem is there in this binary search code. We'll see. Array start, end and target. If start is less than 0 or end is greater than equal to array dot length, we just return -1. Sure. Target index. Okay, this is our target index, and we are going to return that while start is less than end, you grab the middle element, start plus end minus start plus 1. Start minus start plus end divided by 2. If the array of mid is greater than target, then we move the end to -1. Else if array of mid is less than target, we do mid plus 1, right? Otherwise we have found our target index, that is mid, and we break out of it. Looks right. Okay, sorry. No. Start and end movement is there, right? And we are doing return. Looks right to me. We would have to do a little bit of sanity check. Right line, target index left. Let's see the value that we get in this. It'll be -1. Target std output is -1. Okay, so and what about the boundary index? Are we getting the right boundary index. Boundary index is 4, 0, 1, 2, 3, 4. So we are getting the boundary index correctly. So in this one, our first step is right. Define the two sorted array is right. Problem is most probably with binary search. Sure. So we can just remove it from here. Okay. Also, we'll say boundary index to nums length minus 1 start and end. Yeah. What is the problem with this binary search code? If start is less than equal to 0 or end is greater than equal to array length, we have this target index. Yep. So the first time we enter with 4, 5, 6, 7, it is going to say -1, that is completely fine. The second time it entered with 0, 1 and 2, right? The mid will be start, that is 0 plus end minus start. End is okay. Actually, it is going to enter with, let's take this example. I'm going to clean this up and let's understand what is the problem in that code. Okay, so it is 4, 5, 6, 7, 0, 1 and 2, and we've got the boundary index as 4, 0, 1, 2, 3, 4. Fine. And yeah, the first binary search was binary search array starting from 0 till 4 minus 1, that is 3. And the second binary search was array with boundary index plus what was the second search? Boundary index to nums length minus 1. So boundary index is 4, nums length minus 1 is 4, 3, 7, 7 minus 1, 6, right? Okay, the problem is why this one returned -1. It should have returned this value. Let's find that out. So when we, let's try to do dry run of this binary search for that. So we have four, the indexes are 4, 5 and 6 of the three elements when we push them. So middle is going to be start plus n minus start plus 1, and minus start plus 1 divided by 2, uh, 2 plus 1, 3, 3 divided by 2 would be 1, 1 plus 4, that is 5. So mid is going to be this one, fifth index. So we are saying if array of mid is greater than target, so array of mid will be 1, 1 is greater than 0, so we do end as mid minus 1. So end is going to be here, and oh, so the problem is the start and the end are pointing to the same number. Okay, sure, start and end are going to point, it is possible for them to point to the same number. Okay, so we have to do while start is less than equal to the end. Yeah, we have to grab if let's say the size of the array is 1, we still have to find it, find our target in that, right? So our mid, if start is equal to end, would be, so in this case, let's say start and end are same, the index is 4, so our mid is going to be uh, start plus end minus start plus 1 divided by 2, and this is going to be half, it rounds off an integer, so it is 0. Actually, yeah, it is going to be 0, this is 4, so overall mid is going to be 4. Yeah, sure, let's try this. At least binary search should start working, we'll see. Sure. Okay, so we did get the right result for this one. Let's submit it and see. Yeah, am I missing any boundary cases? So let's submit this. It looks good. I'll say. Okay, it has been submitted and it has been accepted. Runtime is okay, fine. So that was the problem. Overall, we have followed all the three steps. Find the boundary index, right? uh, this one, just iterate through it, the first drop in the value, right? That is the boundary index. Then define the two sorted array. We defined two binary searches, although we didn't exactly initialize to array or assign memory location to it or something. We defined it in this way, that what indexes we have to send to the binary search, right? And yeah, this worked. Let's Do we have any other way to work it out? We'll look at that maybe later. Okay, thank you.